I just wanted to give a little help on problems 28 and 29 for 7.4. So I'm not going to go through the whole thing, but I'll give some explanation. So 28, if A is an invertible matrix with the singular value decomposition of A equaling U sigma VT, show that this is invertible. So it said A is invertible, so we know this is invertible. So here, A sigma, if you look at the size, you know the size has to be the same as A. If A is invertible, then A is square. And think about what you know about an invertible matrix and the singular values of A, because the sigma is a singular matrix, and it's a diagonal matrix with the singular values down the diagonal. So that's a little hint on the first part. And show that A inverse equals V sigma inverse UT. So you need to show that A inverse equals this. So that's one part. But then also show that this is a singular value decomposition. The part of the right is the singular value decomposition of A inverse. To show that A inverse equals this, it's easy. The best place to start is just inverting both sides here and then using the properties of inverses. The second piece, to show that this is a singular value decomposition, you have to show that this is an M by M orthogonal matrix. You have to show this is an N by N orthogonal matrix, and that's A is, in general, A equals U sigma VT. This is for an M by N matrix here. You know something more because if A is invertible, you know the size of A inverse. So you have to show that this is that V, or this left matrix, is an orthogonal matrix that has the same number of rows as A inverse, and this is the same number of U is an orthogonal matrix that has the same number of columns. And orthogonal matrices are always square, so you can use that fact. And that's pretty easy because of what you know about the sizes and the sizes of A inverse and the size of A, and what you know from up here. But this, you have to show, so we're showing that this is a singular value decomposition. There's three things to show. You have to show this part about V, this part about U, and you have to show that sigma inverse is a diagonal matrix with the singular values of A inverse down the diagonal. So those are the three things you need to show. These first two are pretty straightforward because you get most of that information from knowing that A is invertible and U sigma V transpose is the singular value decomposition of A. Okay, so for 29, show that, so if A is a U sigma VT, so if this is a singular value decomposition of A, then the left singular vectors, so that's the columns of U are the left singular vectors. So show that the left singular vectors are eigenvectors of A transpose. So you want to show that A transpose times UI equals, well, you can go back to the definition here and try this, equals some sigma times UI. That's the definition of an eigenvector. But it's easier to go back to what we know about V. How do we generate V? Well, the columns of V are the eigenvectors of A transpose A. So you already know that the eigenvectors, because that's the way we generate V, is we find the eigenvectors of A transpose A. So so you can actually get it quicker if you think about, if you do the transpose of A transpose A and think about that. So, and connect it back to this. So there's some hints on 28 and 29. Thanks.